Next speaker, Graeme from Columbia University, is going to talk about a resource sharing model in local time interactions. I'm looking forward to the talk.
Thank you. Thank you to the organizers. It's fantastic to have this opportunity to speak. Sharing this model today, resource sharing model in the context of systemic risk with local time interactions. So we'll divide this into three parts. There will be an interacting particle system, and then we'll look at the mean field limits, and then we'll compare it to some other models and discuss some next steps. So systemic risk, we want to very broadly separate two classes of model, bail out and bail in. So this slide's very conceptual, bear with me. This was the equation I was afraid of writing down. It's just a difference, but we conceptualize the capital buffers of n firms as the difference of assets and debt. So we can think of these firms as globally systemically important banks. And in a systemic risk context, we're worried about these things going to zero. And so we'll take this equation and we'll assume some sort of dynamics on it. And so here, we've split this into two parts. The first part is some stochastic evolution for the assets. You take your funds and you invest them. And the second part here will be the evolution of the debt. And depending on the model, we'll have a different evolution. And so in a bail out model, these CIs typically are transfers coming from the government when your capital buffers are low to keep you solvent. In a bail-in model, which we'll discuss today, these will be transfers between the firms. And so this will be accomplished through loss-absorbing capital, senior debt, between the banks. And it's going to be done in a very specific way after this slide. So these Zs are driving processes. And today we're going to take them as Brownian motions. And we'll get some very interesting behavior just with Brownian motions. Of course, we can put diffusions here, common noise, and talk about these things another day. So let's go into the specific bail-in model. So again, we have our driving process, initial data plus Brownian motion. And this last part here is our CI. This is our bail-in. So we have this LI term. This is going to be a reflection term that keeps the capital buffer non-negative, LI for local time. And we subtract from the capital buffer of each firm alpha n-1 inverse times the sum of the local times of the other firms. So this is the bail-in agreement. You can think of it as an insurance type of setup. I pay a little bit towards your reflection term, and in return, I'll get a reflection term when my capital buffer is at zero. And so the B's are Brownian motions. You could say it's the Bachelier model. And the L's are local times. So they'll satisfy this Skorohod equation, but we'll have n coupled Skorohod equations. So there's some work to do to show that we have existence, uniqueness to this system. These things I've been saying. I've also fixed a parameter alpha here. And so this, when alpha is 1, we'll have pure transfers between firms, a conservation of mass or conservation of capital. When alpha is less than 1, you have to give up less than $1 for someone else to receive a full dollar. And when alpha is greater than 1, there will be friction in the system. And so we can realize these XIs as the components of a reflected Brownian motion. So here we go. This is somewhat classical at this point, semi-martingale reflected Brownian motion in the positive orthant. This comes up in stochastic portfolio theory. So we take this matrix Q that's encoding this relationship between the firms. It's going to be 0 on the diagonal and take value n-1 inverse otherwise. And so if we look at this semi-martingale reflected Brownian motion with matrix R, identity minus alpha Q, we want to satisfy the semi-martingale decomposition, initial data, n-dimensional Brownian motion, and then this reflection term. So the matrix R times this vector of L's. So each Li satisfies these same things that we want for a one-dimensional reflection for the Skor-Hott equation. They start from 0, they're continuous, non-decreasing, and Li only increases when x is on the face where xi is 0. And so this is the zero-off condition that we're familiar with from the one-dimensional reflected Brownian motion. So as I said, this is classical. In the case alpha is less than 1, this goes back to the 80s. And what we've done new today is expand this by pushing to the alpha greater than equal 1 case. So what happens? Alpha less than 1 has been known for a long time that there exists unique strong solutions to this system. However, what happens is once you hit this time, tau alpha, where a proportion of the firms, 1 over alpha proportion, is equal to 0, it's been known that this system fails to admit solutions past that time. And so we're going to look at solutions for all time in this range of alpha. Alpha is our critical parameter, and when it's greater than 1, we're going to look at solutions up until this time and stop the process. And so we look at this in systemic risk as the systemic time where the bail-in fails. We can't continue past it. And tau alpha happens to be the maximal interval of existence. So I'll go a little bit into the idea of the proof because I think it reinforces this idea, not just that the math fails at time tau alpha, but that really this would be a systemic time where the bail-in can't proceed. So again, alpha less than 1, we have that this alpha Q matrix is substochastic. This result of Harrison and Riemann from 1981 applies. You get a contraction mapping, everything's great. When alpha is greater than or equal to 1, the matrix R fails to be completely S. I won't go into the definition of this, but in this case, you can't have global and time solutions. However, alpha Q prior to this stopping time, only less than 1 over alpha proportion of the firms are touching 0. And so the local time terms that are active are less than that amount. And so alpha Q is effectively substochastic prior to this time. So again, I'm giving you ideas from the proof, not the proof itself, but effectively substochastic if that notion makes sense. And so we'll look specifically at alpha equals 1. In this case, we look at the total capital in the system, YT. And in this case, the transfers cancel out. And so the total capital evolves like a scaled Brownian motion. So time tau 1, this is when all of the firms, when alpha is 1, are at 0. Okay. However, the total capital looks like a Brownian motion. And so we can't continue past this time because we know that a Brownian motion in a right interval of 0 has to go negative. Okay. And so this is how we get the maximality of that time. And we look at a subsystem to show that this is a maximal time when alpha is greater than 1. Great. So we have existence and uniqueness of this, this system. It turns out to be a semi-martingale reflected Brownian motion. And now we're going to pass to the mean field limit. We'll be able to prove some interesting things, and then we'll be able to go back and compare the finite particle system and the mean field limit. So we look at this empirical measure, mu Tn, of the firms 1 through n. And we see that our systemic time can be phrased as the first time that the empirical measure places mass greater than 1 over alpha at the origin. This is our equation in components for our bail-in model. And so we'll formally at first, right, we have to show that there actually exists some notion of solution to this, but formally at first, we just take these empirical sums and we replace them by expectations. So we have 1 here and another one inside the brackets for this score-hot equation. So this is what we expect a representative firm to do in the mean field limits. And this time tau alpha, now mu will be deterministic in the mean field. And so this will be a deterministic time, the first time that the law of xt places mass more than 1 over alpha at the origin.
Yep. X bar 0 has some initial distribution.
Yeah, so when we do the propagation of chaos result, so this is one dimensional. We'll just take x bar 0 to be x0i. So we can take these guys as IID, and we can start by the same initial condition. And this B, I've overloaded the notation. This is a one-dimensional Brownian motion. Yeah, thank you for the clarification. Yep. Yeah. Yeah. So we'll see on the next slide. Yeah. We'll see on the next slide. This is there's another way of looking at this through PDEs, of course. In this case, you get a singular PDE, and this is a singularity at the origin. So prior to the blowup time, you shouldn't have mass at 0. Right? So there's another talk I could give that looks fully at the PDEs, and we'll see a little bit of a hint towards that on the next slide. But this is a singular behavior. Yeah. And so this is our notion of solution to that equation. So again, we have it down here. What we do is we take a candidate free boundary, script L, and a candidate terminal time, capital T. So script L being very general, CAD lag, non-decreasing. And we look at this system, we've replaced the expectation just with script L. And we'll say that L and T solve, we'll call this the nonlinear score-hot equation if these equations are satisfied for given Brownian motion. And this consistency condition, script LT has to be the expectation of the local time LT. So firstly, if we start without too much mass at 0, then solutions exist. So there will be some time t. They will be continuous. And also prior to time capital T, the mass at the origin will be subcritical. Furthermore, if we take two solutions, LT, L tilde, T tilde, then they agree. We have uniqueness on the intersection of their intervals of existence. Here's the theorem, again, assuming that the initial mass is subcritical, then there is a unique maximal solution to this problem, maximal in the sense of time interval. And moreover, what happens at the left limit, at time t minus, we have that the mass at the origin is 1 over alpha. And so with this known, we can go back and justify solving this system here on this time interval. And indeed, the terminal time will be the first time that the mass at the origin exceeds 1 over alpha. And this is a good problem as well that Nazar raises. It relates to the particle system, the existence of macroscopic simultaneous collisions at the origin, right? So in stochastic portfolio theory, you look for conditions so that you don't have triple collisions. This mass at the origin, right? You could think this, if you can have simultaneous collisions of a macroscopic number of firms at the origin, this could pass the mean field limit here. So what can we say? We get a lot very nicely for free looking at the mean field equation. The first thing, we just take the expectation, okay? And we get a lot of interesting data. So again, we're assuming that there's not too much mass at time 0. We take the maximal solution from the previous slide, take the expectation, and we get the following. So if alpha is 1, right, pure transfers, then the expected capital is conserved. If alpha is less than 1, this subcritical case, then money's being pumped into the system. This is the subsidy case. And if alpha is greater than 1, then the expectation goes to 0. You have to have this time of failure because X is a reflected process, it's non-negative. And so related, the existence times, when alpha is 1, we have that the terminal time is finite. When alpha is less than 1, the terminal time is infinite. This agrees with the finite particle model. But at criticality, this interesting behavior arrives. Alpha equal to 1, we had that, we compared this to a Brownian motion, right? This was the first return time of a scaled Brownian motion at the origin, and this was finite almost surely. However, in the mean field limits, we see that the average capitalization, right? It is the scaled Brownian motion. We can apply the reflection principle to look at the first time it hits 0. If we fix n and send t to infinity, then this goes to 1. But if we fix t, look at a fixed interval, and send n to infinity, this goes to 0. And so I'll come back and discuss an up the river problem at the end of this talk. In that case, they send t to infinity first, and then n to infinity, and they get a pessimistic result. Here, first we fix t, send n to infinity. We see that the capital is conserved for all time. There's no systemic risk. This beautiful thing happens, and then we take t to infinity. So there's some questions there that, how to extend the model to bring default risk back into things. So we can say even more. And this, we'd have to go to the PDE universe to understand where these nice distributions come from. But we have convergence to some very nice distributions. So in the alpha equals 1 case, we had that the capital was conserved. And if we take a finite second moments, then we even have that the capital converges in Wasserstein distance to an exponential distribution. So this is very interesting, right? It says, after a long time, we expect these to be the relative capital buffers of the firms. When alpha is less than 1, this is when we're pumping money into the system. The expectation is increasing, so we're looking at the relative capital buffer. So this gives us a self-similar solution, and VT again converges in Wasserstein distance to this distribution, right? So this kind of looks like a Gaussian, but it's confined to the non-negative numbers, and this C is a constant that makes this a probability density. So that's fantastic. Working on this project kind of convinced me that going to the mean field, you can get some things very simply and very easily and very beautifully, because sometimes you see some mean field talks and it's not immediately clear, why you would want to do this. But I think when you see, okay, this tells us exactly what the long-term capital distribution looks like, this is kind of a nice thing. And so to relate it back to the finite system, here we only look at this subsidy case alpha less than 1 because we want to have, we don't want this blow up to happen. This is the singular behavior that complicates things. So this is a work in progress. It's only a proposition about propagation chaos, not a theorem yet, because I'm still looking at this alpha greater than or equal 1 case. If we take our IID initial conditions and drive the particle system by an n-dimensional Brownian motion, and we take a tuple of solutions to the mean field problem with the same initial data, like Sebastian asked, and the same Brownian motions, then we get this thing, if you look at Snitman's book on propagation of chaos, he calls this trajectorial convergence. And so it says that a firm from our particle system looks close to a representative firm from the mean field system. Okay, and so we come to the last part, comparisons. Started by talking about bail-in and bail-out. This was the original motivation for this project, was this bailout up the river problem of Aldous, which was solved in this paper by Tang and Tsai in 2018. And so here we have this evolution of the capital buffer, initial condition, Brownian motion. And now these CIs are transfers from the government. And in this case, there's a default risk at time tau I, the hitting time of 0. If your capital buffer goes to 0, then you're out of the game. And so the central planner has to decide how to divvy up this unit of drift between the n firms and wants to optimize the number of surviving firms. Okay, and so the inspiration for this local time model is, well, if we don't have this condition, right, and if we let our phi's be singular, we can just give everyone a local time, right? And at what cost? We have these transfers that tell us, friction, subsidy, zero-sum case, how the debt should be forgiven, the loss absorbing capital. And so in this case, the number of particles that you can keep alive forever is on the order square root n with high probability. And this is achieved by giving all of the drift to the particles at 0. Okay, and so you can compare this to our model. We're kind of doing the same thing, only instead of a drift, we have this local time, right? This strange singular thing that we're giving to the least particles. One other comparison is Atlas models from stochastic portfolio theory. And we're going to hear a talk about rank-based models with common noise. And I think this would be a nice place to take this free boundary problem. We'll just look prior to the first triple collision at 0 for ease. Before this time, the ranked capital buffers satisfy this system of SDE. So this looks a lot like the Atlas model, right? We're driven by Brownian motions. We get pushed up 1/2 when we collide with the particle below us. This is the top particle, so it only gets pushed up. Particles in the middle get pushed down as well. And the least particle gets pushed down. But the least particle is playing the role of Atlas, and he'll get pushed up by the full local time at the origin. This is our reflection. And we'll subtract that local time, a share of it from everyone else. So perhaps seeing this convince you that it's not an Atlas-like model, but an Atlantic model, as Yanis Gratsis would describe it, which I realize now is like the Greek root word for having to do with Atlas. So there's more work to be done here. So just to conclude, going back to our original motivation with the globally systemically important banks, typically only 20%, no more, is this loss absorbing capital. And so this model, we're letting time go to infinity. We're continuing this bail-in scheme forever. What happens when we run out of loss absorbing capital, adding back in this possibility of default? Again, with the Atlas model, this tells us that we could consider this with a ranked-based bailout. So, the one easy one is you can put the reflection term for the least guy at the top guy and do a Bernie Sanders type, the 1% pays everything sort of thing. That's an interesting problem. The equilibrium measure you get there is uniform. And so there's fun PDE questions here as well. So how do these modifications affect the long-term behavior of the model? Also the possibility of singularities, both for the finite and for the mean field model, and what's desirable bail-in strategy from a regulator's perspective and also the perspective of an individual firm. So that's all. Thank you.
Thank you very much. Are there questions?